In this work, we present Multiplicative Controller Fusion, a method for leveraging algorithmic priors for sample-efficient reinforcement learning and safe sim-to-real transfer. Standard reactive navigation strategies that exhibit a high level of efficiency and dexterity when avoiding obstacles are difficult to handcraft and may require significant amounts of tuning to suit a particular environment. However, they are deterministic and still exhibit a competent level of obstacle avoidance across domains. Note the inefficient oscillatory behavior as shown in the video. End-to-end navigation strategies learned by deep reinforcement learning methods allow the robot to learn such complex and efficient behaviors through environmental experience. Note the dexterous maneuverability of the agent in the video. They however require significant amounts of online training and often overfit to their training environment, making them unsafe for deployment in the real world. We take a step towards addressing these limitations by leveraging these classical controllers as priors for increased sample efficiency during training and safe deployment in the real world. We propose Multiplicative Controller Fusion, a strategy to fuse a stochastic reinforcement learned policy and a classical controller in order to attain the desired performance. The general form of MCF is given below. We begin by describing how we utilize this formulation to improve the sample efficiency during training. Standard exploration techniques such as Gaussian exploration used by stochastic policies require significant amounts of environment interaction before obtaining a reward. This is made significantly difficult in long-horizon sparse reward settings. We see the agent exhaustively exploring regions of the state space which are not particularly relevant towards solving the task. The image denotes the regions visited by the agent after 50,000 steps for the point goal navigation task involving a long-horizon sparse reward. An alternative is to utilize the vast range of deterministic algorithmic priors and controllers available to provide a soft constraint on exploration by guiding the agent during the initial stages of training. This provides a positive bias to exploration towards the most relevant regions of the state action space. We utilize a gated variant of the general MCF equation as shown. The system consists of a distribution over actions from both the prior and the policy. The gating function alpha biases the resulting sampling distribution towards the prior initially and gradually shifts towards the policy. This allows the policy to improve beyond the performance of the prior and correct for any extrapolation errors. For a fixed start and goal position, we show the state space coverage using MCF after 5,000 steps. Note how it is capable of exploring the relevant surrounding regions of the state action space for potential improvements. The training curves illustrate the key advantages of our approach, which is shown in yellow. Note how it quickly converges to the lowest episode length when compared with standard end-to-end based approaches. Additionally, it illustrates that MCF was able to surpass the performance of the prior controller used. We note that the gating function plays a particularly important role to this effect. The graphs also show that MCF significantly reduces the variance across multiple seeds when compared to the baselines and standard end-to-end methods. At deployment, we propose the architecture shown to allow for efficient and uncertainty-aware navigation of simulation-trained policies deployed in the real world. We achieve this by exploiting the deterministic and safety characteristics of a handcrafted prior as a reliable fallback for the policy in states of high epistemic uncertainty. Simultaneously, we gain the efficiency and dexterity of our trained policy in states that it generalized well to. We capture the epistemic uncertainty of the policy by deriving a new distribution from an ensemble of trained policies. This new distribution captures the confidence of the policy to act in a given state. High uncertainty could result in unsafe behaviors. We derive a distribution for our prior controller output using Monte Carlo sampling of our noisy laser scan outputs through the prior controller. The two distributions are then multiplicatively fused, and the composite distribution exhibits the safest and most efficient action for execution in a given state. The mean of this distribution is then executed on the robot. Here we show the prior controller directly deployed on a real robot. It exhibits inefficient oscillatory motions as it moves along the corridor. Our approach attains a smoother control signal as a result of the trained policy improving beyond the suboptimalities of the prior. This allows it to efficiently navigate along the corridor. We show how MCF allows us to gain the efficiency from the policy whilst allowing for safer performance in cases of high policy uncertainty. Note how the robot relies heavily on the prior during the initial movements before gaining familiarity with the surroundings and allowing the policy to have an influence. The table summarizes the results obtained for a navigation task in the real world. The task was deemed unsuccessful if a collision occurred along the trajectory. MCF is shown to significantly outperform both the prior and an end-to-end trained policy, which failed to complete both test trajectories successfully. We also show competitive results when compared to a well-tuned IROS move-based controller. We take a closer look at the trajectories attained using each controller to better understand the results in the table. We firstly compare MCF and the prior controller. Note the smoother trajectory obtained by MCF as indicated by the less pronounced trajectory plot. The darker regions in the prior's trajectory indicate areas of high oscillatory behavior along the path, resulting in a longer actuation time to complete the task. MCF allows the policy to naturally fall back to the prior controller in states of higher uncertainty. Note that these are regions that the policy alone failed, indicating states that the policy may have not generalized to during training in the simulation environment. For more details, please refer to our paper and code available on our project site. Thank you for listening.